In this video, we'll introduce the concept of pooling and subsampling from convolutional neural networks. So we're ready now to look at this third idea that characterizes convolutional neural networks, which is the idea of pooling and subsampling hidden units in convolutional neural net. So we saw before, thanks to the local connectivity of the hidden units and with parameter sharing, that we could compute the activation of a hidden layer of a convolutional neural network by doing multiple convolutions, one for each input channel between the input channel and some feature map, summing over all the input channels to aggregate all the pre-activations from all the input channels, and then applying, like we usually do in feed-forward neural network, some nonlinearity on the pre-activations, and then that would give us the activation of the hidden units in some given feature map. So this formula might characterize for 1j the value of the feature map, and then we would have in the whole hidden layer usually multiple feature maps. So we'd repeat this operation but with different convolutional kernels, so with different hidden weights matrix wij. And so this operation of multiple convolutions with nonlinearity would define the activation value of a convolutional hidden layer. Now on top of this, we'll usually add another operation, which we call pooling and subsampling. So I'll first define what it does, and then I'll describe intuitively why it's a good thing to have. The idea of pooling is essentially corresponds to taking a set of hidden units and aggregating their activation somehow to obtain just a single number. So one thing we could do, and this is referred to as max pooling, is to take all the hidden units in some given feature map that are in the same local region. So remember, feature map, we can think of it as an image, so they're locally placed in the feature map, so we can take just a patch in it, or if you want to think about it as a receptive field, and then in that region, taking all of the activations of the hidden unit with max pooling would be just taking only taking the maximum value of all the hidden units, which is illustrated here. So with some index P and Q, which indexes some local neighborhood in some region in a feature map, we just take the maximum value in that local neighborhood. And that would then become the new value at a given position in the subsequent layer of our convolutional neural network. And this pooling operation, we would normally do it over non-overlapping neighborhoods. So if we have a big feature map, we could say divide it into 3, like this, and then in each neighborhood, we would actually take individually for each neighborhood the maximum, and that would give us, say maybe this image was like 9 by 9 for this, say this was a feature map that was 9 by 9, so there were actually 3 activations within each neighborhood. Then after the pooling operation, because we did a max over non-overlapping neighborhoods, we would actually get a matrix that's only 3 by 3. Okay, and then each value here would be the maximum activation within the corresponding local neighborhood. So that's why we say it's pooling. The pooling corresponds to taking the max, and then subsampling because we have a smaller matrix with fewer rows and columns after we've done this operation. So just notice also, again, I'm using the notation from Jared. The way to define the different operations is that the input of the operation is always x, and then the output is always y. So x here would actually be, from my previous slide, the computation of these convolutions plus nonlinearity. So this would be the x that we see here, and then we get an additional, subsequent layer here, which would be the pooling subsampling layer, which would correspond in this case to doing max pooling. Another variant or an alternative of the max pooling is to do average pooling. So if the size of the neighborhood over which I'm doing pooling is m, then I just take the average of all the activations in that neighborhood. So I would take the sum and divide it by m squared. So that's called average pooling instead of max pooling. Now, there are certain advantages to pooling subsampling operation. The first one, which is perhaps the most obvious, is that it reduces the number of hidden units in the next hidden layer. And this is because of the subsampling operation, essentially. And if on that hidden layer we were to then perform some more convolutions with nonlinearity, then this means that computing this subsequent convolutional layer will be more efficient, because there will be the size of the feature maps that are fed as input to these new convolutions will be smaller, so it will be more efficient to compute. So that's a first advantage. Another advantage is that it introduces some invariance to local translations. And that's actually mostly true for the max operation. So essentially, if the maximum value in some neighborhood doesn't change after we apply on the image a small translation, in other words, if the maximum value in the neighborhood still remains in the same neighborhood after the translation, it means that after pooling, the value of the pooled value will not change, because the max is still the same. And so intuitively, it means that if we have local translations like this, where the max remains in the same local neighborhoods everywhere, then it means we get exactly the same pooled and subsample hidden layer in the convolutional neural network. So this way, we're able to build some sort of local translation invariance, which is useful for convolutional neural networks, because for object recognition, say, because the position of the object does not necessarily define the actual identity of the object. So here's an example of two images over which we performed a convolution followed by max pooling. So this is actually the next step after the convolution we saw in the previous video, where we did a convolution with a filter with 0, 0, 0.5, 0.5, and then we applied some nonlinearity. Well, it turns out if I do this convolution plus nonlinearity and then I do a max pooling operation, I get exactly the same pooled value of pooled and subsample value of the hidden layer for both these images. And so, in this case, it's hard to see how both would be somewhat equivalent. They are equivalent in the sense that both have nothing happening here. The only thing that moved really is this that went up. And so this was this. And then we see that the hidden layer sort of reflected the fact that nothing changed really up to very small local translation operations.